Assalamualaikum and greetings. I am NURUL and the title of my final year project would be the investigation of aerodynamic and stability performance of wing in-ground effect craft. Presented in the first slide is a brief introduction of wing in-ground effect crafts or weak crafts. A weak craft is a vehicle which operates above a plane surface without continuous contact with the surface. The ground effect is attributed to the existence of a surface beneath the wing, be it water or ground. In typical flight beyond ground effect, air flows from the region of higher pressure underneath the wings to lower pressure on top of the wings, which produces lifts and also wingtip vortices. Similar phenomena take place for weak crafts as well, but as seen in Figure 1, as it gets closer to the surface, the vortices have insufficient space to expand and gets compressed, causing the air to push towards the surface and the wings, resulting in higher lifts and less induced drag for the vehicle. Next, we will go through the problem statement of this project. According to BBC, air transportation is responsible for around 5% of global warming throughout the decades. From Figure 2, it can be concluded that the aviation industry is responsible for a fair amount of carbon dioxide emissions due to fossil fuel combustion. Therefore, weak crafts are envisioned as a feasible mode of air transportation option as it utilizes the ground effect which enhances the efficiency of an aircraft. Moreover, due to their steady speed and great fuel efficiency, weak crafts are perceived as a viable air transportation option. And unfortunately, researchers stated that weak crafts are not financially feasible for public transportation owing to the complexity in controlling its static stability outside of ground effect. The Federal Aviation Authority stated that the ground effect can have detrimental and unanticipated effects on aircraft, especially in the moments where the aircraft is most vulnerable, such as during takeoff and landing. Therefore, in an effort to encourage the advancement of weak crafts, this project offers an aerodynamic performance and static stability analysis based on previous papers to disclose the existing research findings, and in return, this project may be utilized as a reference for future research and analysis on weak crafts. Subsequently are the aim, objectives, and scope set for this project. So the aim of this project is to investigate the aerodynamic performance and static stability of a weak craft in various height-to-quad ratio or H/C conditions. Consequently, the objectives are as follows. And then the scope and limitations set for this project would be that it involves CFD simulation only, where the aerodynamic performance and static stability analysis is done on ANSYS Fluent. The simulation is also done on the whole craft of a scaled existing weak craft model with NACA 441-2A4. The scaled model used Reynolds number. The free stream velocity is constant throughout the project as calculated in the report. The aerodynamic performance and static stability of the scaled weak craft model is investigated in various height-to-quad ratio or H/C conditions. Moving on to the next part of the project, which is the literature review. So the literature review is done on 5 areas, which is aerodynamics in general, the ground effect, aerodynamic efficiency in ground effect, stability and control in ground effect, and also current technology and research. A conclusion is also provided from the literature review findings. So from the literature review, in terms of aerodynamic efficiency in ground effect, it is observed that all of the papers listed in Table 1 has the same conclusion, which is the lift coefficient increases and drag coefficient decreases as height-to-quad ratio decreases, which means as the craft gets closer to the ground, its lift increases and drag decreases, achieving optimum aerodynamic performance. Meanwhile, in terms of stability and control in ground effect, most of the researchers noted that the effect of stability towards various altitude or height-to-quad ratio is not that significant in ground effect, as the CM versus alpha curve of these papers remained to have negative slope at various HOVC conditions in ground effect as seen in Table 2. However, Only few papers compared the craft stability in ground effect and out of ground effect, which is highlighted in the table. And these researchers found that the craft is more statically stable in ground effect compared to free stream condition, possibly to the shift in aerodynamic center as well. And in conclusion, this indicates that weak crafts depend on ground effect to a great extent when it comes to stability. The next topic would be on current technology and research. So throughout the decades, weak crafts evolved as a result of research on aircraft's landing performance in the 1920s. Today, weak crafts takes various shapes and forms and are capable of many things, including recreational air transportation and also cargo. The most recent weak-craft development would be the Airfish 8 by Widgetworks as seen in Figure 4, which is one of the high-performance weak-crafts in the market currently. Next, as seen in Figure 5, we have the UH-18 SPW hoverwing manufactured by Universal Hovercraft. They are modeled upon hovercrafts that were incorporated with detachable wings and a horizontal stabilizer to allow for ground effect flights. It is also important to note that the craft is the inspiration behind the original CAD model that was received in this project, and it needs to be scaled down. Therefore, it is crucial to understand its configuration before proceeding with developing a scaled CAD model. Next, we will proceed with the methodology flowcharts to aid in achieving the aim and objectives of this project. So firstly, we have the general flowchart of this project, where the project begins with obtaining the configuration of a weak craft design and then proceed with analyzing the model's aerodynamic performance in various HOC conditions, and lastly to compare the findings with existing research papers to validate the results. And with that in mind, a more specific flowchart is come up with for CFD simulation of the weak craft model. Now, before the analysis begins, a CAD model is needed to be developed. So in this project, as seen in Figure 6, a full-sized CAD model of a weak craft inspired by the UH-18 SPW hoverwing as seen earlier is obtained, and its geometry and configuration is recorded in order to develop the scaled model as seen in Figure 7. The ratio of 1:6 is used to scale down the model with the aim of simplifying the simulation processes on ANSYS Fluent, and also to hopefully serve as a reference for the fabrication of RC models to be used in test flights for future research. For the CFD analysis, ANSYS Fluent was used to run a series of simulations on a scaled weak-craft model. ANSYS Fluent is used as it can efficiently retrieve the key parameters of this project, which is lift, drag, and moment coefficients acting on the weak craft. And as stated in the report, before setting up the meshing, the boundary conditions are calculated, such as the Reynolds number, free stream velocity, boundary layer thickness, and etc. Then a computational domain, as shown in Figure 8, was modeled by subtracting the craft from a rectangular block, and the distance to the ground plane was defined by the height to chord ratio, with the height being the distance from the trailing edge of the wing to the ground. And as seen in Table 4, the simulations will be carried out at a Reynolds number of 2.33 times 10 to the power of 6, correlating to its wing mean aerodynamic chord, and a free stream velocity of 110 meters per second as calculated in the appendix part of the report. The next section would be on results and discussion. First and foremost, as the simulation is completed, it is important to validate the results obtained to ensure the accuracy and dependability of the data generated. So in this project, the results obtained are compared with a published paper by Morris et al., where the model and boundary conditions are identical, but the analysis is done in a wind tunnel for realistic portrayal of the ground effect. And as observed in both figures, the two lines illustrate the data derived from ANSYS simulation and the data obtained by Morris et al. In a wind tunnel on a weak craft model with similar airfoil, which is the NACA 4412, with similar boundary conditions and also HOC conditions. The model size, however, differs slightly since Morris et al. Performed the test using a 30 cm wingspan model, whereas the CFD simulation was performed with a 60 cm wingspan model. From figure 9 at HOC equals to 0.303, it can be observed that the data obtained is stable and followed the trend for Morris et al. Closely, whereas in figure 10 at HOC equals to 0.671, the simulation results skewed marginally from Morris et al. But still feature the same trend line. So collectively, it can be concluded that the results obtained from the simulation are satisfactory and validate the hypothesis well as they are aligned with the results obtained by Morris et al. As hypothesized, flying the craft at different height-to-chord ratio or HOC conditions had a significant effect on the aerodynamic performance of the vehicle. So from the figure, it can be observed that the lift curve slope increased as HOC values decrease, noticeably at higher angles of attack with alpha ranging from 10 degrees to 16 degrees. Referring to figure 11, at alpha equals to 14 degrees, lift coefficient is 1.6325 at the lowest flight elevation where HOC equals to 0.05. Mathematically, this represents a 31% increase from the free-stream flight where CL is only 1.2403. And similarly, at alpha equals to 8 degrees, the lift coefficient of the craft increases by 43% with CL equals to 1.2973 flying at the lowest ground height against free-stream condition with CL equals to 0.9081. Then, varying ground-to-plane heights similarly resulted in a substantial progression in the craft's lift-to-drag ratio. In figure 12 depicts the lift-to-drag ratio, or L over D, plotted as a function of alpha for each of the 4 HOC conditions. As seen in the figure, the L over D values increases as HOC decreases for angle of attack ranging from 0 degrees to 6 degrees. Additionally, the lift-to-drag ratio of the craft peaked at HOC equals to 0.05 with alpha equals to 6 degrees, where its lift-to-drag ratio is 127.6, which is an extreme increment compared to its free-stream counterpart at alpha equals to 6 degrees, where L over D is only 12.87. Whereas beyond alpha equals to 7 degrees, the trend of the plots began to regress, and this is probably due to the effects of stall on the craft and prominently since the vehicle stalls sooner at lower HOC value. So apart from analyzing the impact of varying ground-to-plane heights and angles of attack on lifts and drag, it is also important to analyze the moment coefficients for the studied craft model. The pitching moment coefficient, Cm, is a significant parameter to examine when determining whether the model studied is longitudinally stable. As seen in figure 13, the pitching moment coefficient remains mainly uniform at lower ground plane heights when HOC is equals to 0.05, 0.303, and 0.671. This confirms that altering the ground plane height in ground effect has minimal influence on the tested model. And as we know, longitudinally stable aircraft should have a negative gradient on pitching moment plot. Unfortunately, the gradient of the plot for ground effect flight is positive, signifying that the craft is unstable as seen in the figure. In a contrasting manner, the craft is found to be statically stable while operating in free-stream flight as a negative slope is observed when cruising at angles of attack ranging from negative 6 degrees to 5 degrees for HOC equals to 2.436. As a recap, this project aims to investigate the aerodynamic performance and static stability of a craft in various height-to-chord ratio conditions. And subsequently, the CFD analysis performed on the craft model in ANSYS Fluent proved that lower ground heights or operating the craft at lower height-to-chord ratio conditions had a substantial influence on the vehicle's aerodynamic efficiency. The L over D plot shows that the rise in lift and reduction in drag offers notable benefits in flying quality for weak crafts operating in ground effect. And furthermore, in terms of static stability, it is deduced that changing the ground plane height in ground effect has minor consequences on the tested model, but has a considerable impact in free stream flight. According to the simulation results, the model examined has a positive slope for pitching moment coefficient, reflecting that the weak craft is unstable in ground effect. This also implies that rolling the weak craft in close proximity to the ground is more challenging. Conclusively, the CFD analysis effectively demonstrates the aerodynamic performance and static stability of the weak craft under various height-to-chord ratio conditions. The findings of the thesis suggest that flying in ground effect has several advantages and may be optimized to improve an aircraft's performance in a variety of operational purposes, both military and civilian. The evolution of big craft technology is essential since it will be benefit not only researchers but also the aviation industry and most importantly society. And that will be all for my bachelor project presentation. I would like to take this opportunity to thank Dr. Amzari, Mr. Afifi, and Colonel Tamizi for their guidance throughout this project. Apologies for any shortcomings on my behalf. Thank you.